So today I want to talk about chords and distance. So I want to illustrate what I mean by that really quickly before we get started with the notes. So I know you don't have this in front of you, but I just want you to watch. So recall that a chord is just a line segment that extends from one point on the circle to another point on the circle. So I'm going to call this chord AB, line segment AB, and I'm going to call the whole circle, I'm going to name that circle by the center. So I'm going to call that center C, and the way we name circles is we can call it circle C, or you would do the circle symbol C. Now if I want to know the distance from this chord to the center of my circle, there's many ways we could get there. We could travel there from point A, we could travel there from point B, we could travel there from some point along the chord. I'm just choosing randomly now. As you can probably start to see, there's many different ways to travel from the chord to the center of the circle. But the way we're going to go about it today is we essentially want to go from the center of the circle to the chord in the least amount of distance. And that's going to end up being this distance right here. And I'll highlight this in blue as well. So today we're going to get an idea of how we're going to find that distance. So going to your note sheet, in order to start talking about this, I first want to introduce something called the perpendicular chord bisector theorem. This theorem states that if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So make sure you have that written down. And let me highlight what I mean here with this picture. So in this picture, we have that segment EG is the diameter. So I'll highlight that in yellow. Remember, the diameter is a chord that passes through the center of the circle. And then what we have here is a chord, and that chord is in green, segment DF. Now, the diameter EG is perpendicular to chord DF, and we know that because of this 90-degree angle marking. And because of that, we know that segment HD, H to D, is congruent to segment HF, and I'm going to use one tick mark to indicate that. Make sure you're marking this on your paper as well. The second thing I want to point out is that not only are the two segments congruent because the diameter bisects that chord, but also the two arcs are congruent. So arc GD is congruent to arc GF. So we're going to use this perpendicular chord bisector theorem to solve a lot of our problems today. So let's jump to example number 1. This example is asking us to find the measure of arc AB, which is right here. So from the picture and what we're given that arc AD is 65 degrees, and we're also given that chord BD is being perpendicularly bisected. So we can assume that AC will be our diameter in this case, and then we can assume that BD is our chord that's being bisected. Now remember, not only is the chord bisected, but the arc is bisected. So if arc AD is 65 degrees, that means that arc AB will be congruent to that arc, and the measure of arc AB will also be 65 degrees. In example B, we have a diameter, segment FH, and that diameter again is perpendicularly bisecting the chord JG, and that means that from J to E is congruent to segment E to G. So if segment JE is 8, that means that segment EG is also 8, meaning X will be 8. In the last example, again we have a diameter that is bisecting a chord. So we know that this chord is being bisected, and also the arcs are being bisected. So if arc ST is 40 degrees, that means arc RS is also 40 degrees. Moving on to example 2, I'll do letter A with you, and then I want to save B and C for you to do with your groups. So letter A, we are given that we have a diameter segment LN, and that diameter is perpendicularly bisecting the chord MP. So by our theorem that we defined above, we know that these two segments are congruent. And my goal here is to find X and then to find the measurement of the chord MP, or the length, I should say, of the chord MP. So in order to find the length of chord MP, I need to know what X is. So based on this relationship that I know that the chord is being bisected, I can set up an equation that's going to help me find X and ultimately help me find the length of MP. So that equation is going to be, take that 5x minus 6 and equal it to 2x plus 9 and solve for X. So I'll subtract 2x on both sides. I'll add 6 to both sides. And I'll divide by 3 on both sides, leaving me with X is 5. Plugging that 5 in, I get that each segment is 19. Meaning that the whole length of the chord MP is 38. So at this point I want you to pause the video and try examples B and C in your groups. These now are the answers to parts B and C in example number 2. So compare them with what you have on your paper. If they match, that's great, you're ready to move on. If they do not, please address any questions or mistakes you have at this point. So if you want to hit pause while you check, please hit pause now. I want you to flip to the back of your notes page to look at example number 3. I will help you get started with this for part A, and part B I want you to do completely on your own. So I'll help you get started with part A, and part B I want you to completely do on your own. When you're done, you can check the answer key on my website to make sure that you've done them correctly. So for this example, we have that a 24 centimeter chord is in a circle with a radius of 20 centimeters. How far from the center of the circle is the chord? So this is going back to what I originally talked about. What's that distance from the chord to the center of the circle? So I'm first going to use my circle to sketch in my chord. And I'm going to call that chord AB. It doesn't really matter. But I know that that chord, the length of that chord, is 24 centimeters. So I'm going to label that as 24 centimeters. I also know that the radius is 20 centimeters. So if I can connect two radii, I can make a shape that I'm familiar with, and that shape is going to be a triangle. Hopefully you see that. So this radius is 20 centimeters, and that means this radius will also be 20 centimeters. The radius will be the same no matter where the radius is located, as long as it's coming from the center of the circle. Now, using what we learned in the front page, we know that if we were to draw a diameter, that diameter, if it is perpendicular to the chord, and maybe I didn't draw it the best, maybe I'll use a different color as well. So if that diameter is perpendicular to the chord, then we know that the diameter will bisect the chord. So if the whole chord is 24 centimeters, we know that from here to here will be 12 centimeters. And now I'm going to outline this in a different color. I will choose this lighter blue here. We now have a right triangle. Maybe that color was a little too light. I'll choose this teal. We have a right triangle. So the base of that triangle, we can call that X. We don't know what that is, but that's good because that's representing the distance from chord AB to the center of the circle. So this distance we can call X. We know that the height of the right triangle is 12, and we know the hypotenuse is formed by the radius, which is 20. So if I can kind of just sketch this right triangle off to the side, so this is easier to see, the height we said was 12, the base we said we don't know, which is representing the distance from the chord to the center of the circle, is X, and the hypotenuse is 20. So from here, we can use Pythagorean theorem to solve for X. And once we solve for X, we are ultimately finding the distance from chord AB to the center of our circle. So I will save that for you to do on your own, and then try example B on your own as well. When you are finished, check with my answer key on the website to make sure you did it correctly.